Okay, let's get started. As always, let's talk a little bit about deliverables before we get back to lecture. Deliverable 8 is due tonight. How many people have finished Deliverable 8? Hopefully it's relatively painless, right? At least compared to 6 and 7. Okay. Hopefully things are kind of downhill from here. 6 and 7 are usually the monsters. I'll try and make it up for you in 8, 9, and 10. So let's talk about Deliverable 9 for a moment. So Deliverable 7, you are adding state to your program. Deliverable 8, you are adding a database to your program. Deliverable 9, you're going to be adding scaffolding to your program. We mentioned scaffolding last week, I believe. Scaffolding is an idea that comes from developmental psychology, so another aspect of psychology in HCI. Developmental psychology is the study of human development, or the growth from children to adults. Scaffolding is the rather intuitive idea that if you want a learner to learn something, like a child that's trying to learn how to walk, you scaffold their environment. You scaffold the learner's environment to make things simple. Once they start to get a handle on the task, then you gradually start to remove the scaffolding. So, child that's learning to walk, the child stands on mom or dad's feet, mom or dad holds the child and walks the child through the process of walking. So the child's nervous system actually experiences the sensor motor processes involved in walking. Other examples of scaffolding.
Holding the bike while they start learning how to bike.
Holding the bike while they learn to bike, or even better than that, once you get tired of holding the bike.
Training wheels.
Training wheels, right? So training wheels are the canonical example of scaffolding. It exists in lots of aspects of lots of human domains, right? So education. Hopefully the first test or the first deliverable for this class was relatively easy, and I tried to ramp it up to 6 and 7, right? So in interface design, this is an important aspect of HCI. Often you're presenting your user with an interface or a software-hardware combination they've never seen before, like leap motion, and you want them to try and learn how to do something. In this case, they're not only learning how to interact with leap motion, but once they get that under their belts, they're also trying to learn the 10 digits of the ASL language. How can you scaffold that experience for your users? In Deliverable 9, you're going to be shooting some videos demonstrating that you have added some scaffolding to your program, and you're going to be adding 3 different kinds of scaffolds. All 3 of these scaffolds rely on your program's ability to detect that your users are increasing in proficiency. They're getting better at signing the 10 digits. So as your program recognizes that they're getting better, your program is going to gradually remove the training wheels. Okay, so what does this look like? It's only 1 page, so a little bit shorter than usual. But again, this is a little deceptive because most of the onus is on you to figure out the details here. The first scaffold that we're going to be looking for is that you're going to start to present the user with an increasing number of digits. So maybe you roll a 10-sided dice and you choose the digit 7. You show 7 to the user along with a picture of what the gesture for 7 looks like, which I've already forgotten what it is. What's the gesture for 7? This one. Okay, so you show this, the user tries to do it, and they get it wrong, right? The KNN learner consistently outputs a digit other than 7. The user is not getting it. They're not signing that digit correctly. So once they have failed, however you show that to the user, they're presented with 7 again and again and again and again until they get it. Once they get it, now you roll a 9-sided dice and pick one of the other remaining 9 digits. You add that to the set. And now at the next instance, the user is either shown 7 or the new digit, right? And on we go. So you're expanding the digits that you show to the user based on the fact that you've detected that they've gotten better. So you're going to be shooting 1 video to show us this particular scaffold. And in that video, I want to see the user, which is probably you, failing to do what the program is asking and you keep getting shown the same digit. Eventually you get it right once or twice or 3 times or whatever you decide. And now we see that the program detects that and starts to show you a broadening set of digits. Make sense? Okay, that's scaffold number 1. Scaffold number 2 will increasingly challenge the user to remember the gesture associated with the digit as they improve. What might this scaffold look like, and what would it mean to gradually remove this scaffold?
Maybe like have a counter that detects how many times they get it right, and then at a certain amount it stops displaying the image, or I don't know what an in-between step could be from
Okay.
doing it.
So, right, so this is the black art of scaffolding. So we could do what you propose, which is detect that they've signed correctly a few times, and then the next time they see it, they don't get to see the image of the gesture, right? You got the training wheels on and you just take them off completely, right? What we would like to see in Deliverable 9 as best you can is demonstration not just of the removal of the scaffold, but gradual removal of the scaffold. So for scaffold number 1, where you're increasing the number of digits that you show to the user, that one's pretty easy, right? 1 digit, then 2 digits, then 3, then 4, and so on. How might you gradually remove this second scaffold?
You might show it, but not for as long, so it flashes to the user.
Absolutely, right? So flash up the image for a shorter and shorter period of time until you remove the training wheels and you don't show the image at all. That's one way that you might go about doing it, right? You might come up with other ways. It's up to you what the scaffold is and how you remove it, but that's what we're looking for, right? That you found a way to gradually remove scaffolding. Okay, the third one is to increasingly challenge the user to sign the gesture quickly. What might this third scaffold look like, and how would you gradually remove it?
I mean, have like a counter increase each iteration through the program, and then like the fashion they do it, like I don't know, like maybe not let them sign if they don't do it as fast as they previously have, like switch to a different one.
Perhaps, so we might increase the threshold at which we consider success. So if you correctly sign a digit the second time, but it takes you longer, we might count that as a failure. It's one possibility. How else might we do this? You're trying to increasingly incentivize your user to sign more quickly.
Have like a countdown.
Have a countdown, right? That makes sense. Remember our discussion on Monday about perception and attention and memory, right? You can try this yourself. If there's a counter that's counting down, your eyes are going to be saccading to the counter, which is fine, right? But that might add a little bit of stress to the user and make things a little bit more difficult. How would you introduce a timer without actually having seconds that are counting down to 0? What are some other things you might do that allow the user to continuously attend to the wireframe of the hand? How might you do this so you don't have to actually look away from the hand to the counter, which is in the top right?
Have the hand like fade away.
You could have the hand fade away, or the color of the lines might change, or the lines might thicken, or there might be, you could change the wireframe visualization to communicate the fact that there is some timer on the other side that's counting down. And if you do it in the right way, the user will start to get it pretty quickly. They'll build up a mental model, and they'll be able to predict at any instance in time about how much time they have left to sign the current sign. Okay, so you're shooting 3 videos demonstrating these 3 scaffolds, and we want to see the scaffold applied when the user, in each of the 3 videos, we want to see the scaffold applied when the user is failing, and as the user starts to succeed, we want to see in that video evidence that the scaffold is being gradually removed. Make sense? Okay, now performance, detecting improved performance, again, that's up to you. That might be how many times they sign correctly, the time it takes them to sign correctly. It's up to you. We don't care. Any questions about Deliverable 9? No? Okay, so back to lecture. We are working our way through lecture 13. We started a discussion last time about Gestalt perception. What does Gestalt mean? Aside from a word that's fun to say.
Whole is other than the sum of its parts.
The whole is greater than the sum of its parts. Why does that apply to perception? So your users, when they're using the ASL system, they see a set of lines, but they don't see a set of lines. They should pretty much instantaneously see a hand, because the Gestaltists taught us that most of our perception, our brains are wired up to take a whole bunch of disparate detail and immediately see the pattern or the whole that's hidden inside of all of those parts. Okay, so I'm pretty sure we're going to finish lecture 13 today, and we may move on to lecture 14 on affective computing. Okay, so we started last time by looking at Gestalt, and then one of the first rules or laws of the Gestalt approach to perception, which is this idea of reification, which is as close to the philosophy of Gestalt perception as you can get, right? Your brain is reifying or making real the triangle in panel A and the bar in panel B and the sphere in panel C and champ in panel D. Okay. We ended last time by talking a little bit more about, aside from trying to synthesize wholes from perceptual parts, what is the brain really attending to? We finished a discussion about attention last time. There's lots of controversy in the field of psychology because, again, we don't really know how the brain carries these things out. Some psychologists argue that our brains focus on the constancies in our world, and others argue that our brains focus on the changes in the world. And as you can probably anticipate, they're both right. Okay, let's see some examples of this. We're going to see some examples of perceptual constancies and perceptual changes. And in both cases, in the examples I'm about to show you, I want you to pay attention to the context, which is the other perceptual things that are going on that help you make sense of the constancy or the change. Who has seen this optical illusion before? Tell me about the colors or the grayscale of A or B.
The shadow or the light square in the shadow is supposed to be the same color as the dark square outside of the shadow.
Absolutely, right? Oh, the light square, which you said light square and dark square, which is which?
The darker one.
This is a trick question, right?
There's a darker one and a lighter one, and the lighter one in the shadow is the same color as the darker one outside.
Okay, so the lighter one in the shadow, which is panel B there, compared to the darker panel A outside of the shadow.
Oh, there's numbers.
Oh, sorry, you can't see that from back there. There's A or B if you can't see it. A is the darker panel, and B is the lighter panel. There was something incorrect in that statement. What is it? They're the same light intensity, right? Neither is darker than the other. I see a lot of concerned looks, right? A and B are the same color.
I don't believe it.
You don't believe it, right? That's the whole point. None of you should believe it. I promise you that it's true, and I'm about to prove it to you. Trust your professor for a moment. It's true. Your brain is militating against it. Why? Why is your brain convinced that B is lighter than A?
Because there's darker squares around it and the shadow making it seem like it's lighter, whereas the one that's out in the, not beyond the shadow is surrounded by lighter ones, making it seem like it's darker than it actually is.
Right. So the shadow is influencing your perception here, right? That's the context. The context is the shadow.
We're also really used to that pattern, having dark and light operate like that.
There's also that, right? So this panel here is actually lighter than this one. But if you pay attention carefully, these two are the same. All right, here's your proof. This is not unlike the Necker cube, right? Hopefully with these added bars, your brain should be able to grasp for a moment that these are the same color, but the moment your brain loses focus of those two bars, it flips back to B is lighter than A. Let me grab a colored object from up here. Okay, so hopefully most of you can see the medium green on this eraser. If we were to turn off the lights in this room, which is good because there's no windows in here, there would still be a little bit of light filtering in from the two open doors. What color would you see? This room is mostly dark, a little bit of light filtering in. What is the color of this label? It'll be dark green, but your brain will know that it's not actually dark green. Why?
Because we assume
Right.
the light is making it darker.
Absolutely. So the minute we turned off the lights, the early part of your visual stream, the part at the back of your brain, will tell the front of your brain, the conscious part, you're looking at a dark green label. But the front part of your brain knows that I didn't magically change this, the color of this label, the instant we turned off the lights. It's focusing on the constancy of this particular object, this label. Regardless of the light levels that fall on it, you know that this color is probably not changing, right? Even if I change the orientation of it, maybe some self-shadow falls on it, the actual color of this label is changing according to one part of your brain, but the other part is correcting for that change. It's compensating based on its predictions about overall light levels, right? You can imagine why our brains evolved to do that. If you know that berries of just this color of red are safe, and berries that are a slightly different color of red are deadly, and you see those berries in different light levels, your brain needs to be pretty good at knowing the actual color of that berry. So this optical illusion is designed to try and foil that, right? Your brain is constantly lightening the color of panel B because it knows it's in shadow. And then when I ask you to compare these, your brain says B is lighter than A. Right? So this optical illusion is a great example that shows that our brain is always working to compensate for other things that are going on. Okay. What other kinds of constancies exist? Here's another Gestalt Law Perception, which is the law of continuity. I've taken 5 semicircles here, and I've laid them into the slide. And your brain knows that there's a very low probability that these 5 semicircles are lined up corner to corner, assuming I didn't do it on purpose. So instead of 5 semicircles, you probably see what?
Single birding strap.
Some single object here, right? So a twisting piece of paper or a ribbon or something like that, right? So based on the way that these two separate objects are touching one another, it makes it seem to your brain, again, that there is one object there rather than 5. Okay. Why does this matter for HCI? Remember our discussion about visual design. We want to try and communicate as much information as possible with as little ink as possible. Let's imagine that I wanted to create a visualization for our users to communicate some hierarchical structure. There is some top-level object followed by 2 underneath it, and 2 underneath it, and 2 underneath it. So there are 15 objects in total. And in order to communicate the hierarchy or the relationships between them, I might connect the objects that are related with lines, which gives me another 14 perceptual objects, the 14 lines, and a total of 29 visual objects. If I remember the Gestalt Law of Perception and continuity, that things that are close to one another seem to be part of the same whole, I can throw the lines away. And there are actually probably more colored pixels here than there are here. But the idea here is this is somewhat simpler than this. Hopefully, by looking at this, I can convince you of the relationship between these objects. If you look carefully, this pair of objects down here, these two objects are actually closer to one another than either object is to its parent node. But hopefully you get the idea that this one is more related to this object than it is to this object. Make sense? So we can rely on some of these perceptual biases to simplify the way we communicate information to our users. Okay. Here's another one. So we just looked at organization of objects. What about shapes? So here we have a bunch of objects, and hopefully you see 3 rows here rather than 6 columns. I cheated a little bit because the circles actually are physically closer to one another than the circles are to the diamonds. I meant before class to try and equalize these distances. You can try it yourself. I think you will still see 3 rows rather than 6 columns because our brains tend to group together similarly shaped objects. There aren't actually 3 rows here or 6 columns. It's what does your brain tend to see, right? Perception is an active process. Okay. That's the Gestalt Law Perception. Things that are similarly shaped or similarly colored, we tend to see as a group. Closure, another rule, we tend to see objects that are visually ambiguous. Our brain tends to focus on the closed rather than the open. There's another optical illusion for you. What do you see? Yep. There's the vase and the 2 faces, right? So like the Necker cube, your brain should probably flip-flop between seeing the vase for a little while and then seeing the faces. If you pay really close attention, for most people, they tend to spend more time in the phase where they see the vase than they do the 2 faces because the vase is a closed object and the faces, although there are not closed objects, they're open objects. So again, if you display something to your user and they're trying to make sense of your visualization, they will attend to or recognize closed objects more than open objects, which is again something that you can exploit. Okay. We're still talking about constancies here. So what other kinds of constancies are there? We have color constancy, so we tend to see the same color even in changing light levels. And hopefully in this case, when I ask you what is the shape of this object, you won't say an oval, although that's really what you're seeing. What is your brain seeing instead?
Round.
Something that's round. Well, an oval is round also. A disk, right? So there's a circle there. Your brain is taking this object and pushing it through a mental model, and that mental model mentally rotates this coin until it's face on, and your brain knows that when this object becomes face on, it's going to be a circle. Even though you can't see the circle, you see an oval, right? Because you have 20 or 30 years of experience of coin-shaped objects that you see as an oval, and when you rotate them face on, they're a circle. There's another version of this optical illusion where you narrow this image a little bit, and most people will also know that when you rotate it, it's now not a circle but an oval. Okay, so we see objects in different light levels, at different orientations, in different positions. But we know most of the time that that object is not changing when the light levels change, or when the object rotates, or when the object moves. That's not always true. We know that's true of rigid objects, right? So your brain is doing a lot of that work for you already. Okay. Let's switch now from the way in which our brain tends to enforce constancies. And let's switch now and focus on how our brain deals with change. We've already mentioned this a few times already. There's some obvious cues that we pick up from things that are changing in our environment. If we see multiple objects and some of those objects are moving faster than others, then usually we infer that the object is closer. The object that's moving faster is closer to us. That's not always true. It's true in this cartoon. When is that not true? You have a bunch of objects, some of them seem to be moving faster than others, but your brain does not think that the faster objects are closer to you than the slower moving objects. Let's imagine, I should make an animation of this one of these days. Let's imagine I showed you a whole bunch of objects. They were moving at different velocities, but there was no correlation between the direction they were moving. Try and mentally simulate that. What would you take away from that animation? What would your brain tell you it's seeing? Would you feel like some of those objects are closer to you? Yes? No? Usually it's no. Why no? So in this cartoon here, these two trees are moving in the same direction. There's a perfect correlation between their movement. If you ever see in a sci-fi movie, the star field, and they jump to warp drive, and all the stars move away from the center of focus. They're moving in different directions, but their directions are correlated. They're all kind of moving away from the center of the screen. So sometimes it looks like some of those stars are closer to you than others. If everything is moving in different directions, that illusion falls apart. Why? Because what's that?
Because that means that the objects themselves have to be moving. It's not you moving around the object.
Absolutely, right? So if you look out the window at a bunch of trees and all the trees are moving in the same direction, your brain usually knows that it's not them that's moving, it's you, and so that the things that seem to be moving faster are closer to you, right? The stars are actually not moving. It's usually you in the spaceship that's moving forward. If everything is decorrelated, then it's probably the objects that are moving themselves, and you can't then rely on velocity as a cue for which ones are closer to you than others. For those of you that are proficient now in Matplotlib or Pygame, you could probably write such a simulation pretty quickly and try it out yourself. Okay, so remember that all of these perceptual biases come from our decades of experience in the physical world, right? Here's another one that I just mentioned, right? So objects that are flowing from the center of the screen out towards the corners of the screen are usually implying that you're moving in towards the center of the screen. This has been a simple graphics trick in video games since the beginning. Okay, so we've been working our way through memory, attention, and perception, and we've been looking at some of the biases in human perception that we can exploit for HCI. Let's turn things around now. Remember, in human-computer interaction, humans perceive the computer and react to it, but more and more of our apps are also perceiving the human user and reacting to them. And your users usually know that. So they are building up a mental model of the software, the app, or the robot. So we need to think carefully about how apps and combinations of software and hardware perceive the world. This is easiest to do when we think about a robot, which is basically just a computer that can act and perceive the sensory repercussions of its actions, and it's able to physically move as well. Okay, so in order to think about this, let's write a few lines of pseudocode for a very simple robot, which is our Lego robot that we have here. In this cartoon here, we're looking down on the robot from above. Let's imagine that this robot has 2 wheels, and all this robot can do is stay still, turn on the spot, and if it detects that it's in danger, it can drive away. It can run away. So that's all it can do in terms of its motors. We're going to give it just one sensor, which is an ultrasonic sensor. So this is the Lego Mindstorms robot kit. This is what an ultrasonic sensor looks like. The ultrasonic sensor gives information about distance. Let's imagine that the ultrasonic sensor is on the front of the robot. So as it turns, it's sort of scanning how far away any objects are from it. In this little cartoon here, let's imagine that there is only a single moving object in its environment. So if it doesn't see the object, it returns 2 feet, or the sensor returns 2 feet. If it turns and it sees the object, it returns a single number, which is how far from that sensor to the object. So we now know how the robot can move. We know how it can sense. We're going to give it one more item, which is a timer. So it's got a stopwatch. When we start this robot, it starts the stopwatch and it has timing information. So it can record when it detects certain sensory events. So far, so good? Okay, so this cartoon here is to sort of show you what this robot should do. If there's an object here and the robot somehow detects that the object is moving away from it, it should stay still. It's not in danger. In this case, the object starts here and approaches the robot, and the robot should run away. In this third case, which is tricky, the object is here, the object starts moving and actually gets closer to the robot, but it's not in danger. This object is eventually going to miss the robot. So I want you to turn to your neighbor, and I want you to sort of just sketch out a simple algorithm for this robot that will use movement, timing information, and sensation to be able to distinguish between these events. So in essence, the robot is just going to return a binary value. 0 means I know I'm safe, and 1 means I'm going to run away because I'm in danger. This case should return 0. This case should return 0. This case should return a 1. I'll give you a few minutes to talk that over, and then we'll see what you came up with.
So take 2 readings and it's getting closer. And then if it makes a specific boundary, whether or not it's current, current path of the line. This thing's spinning. I think part of the sensor is the robot itself.
Sorry, there's a little bit of a confusion here. So when the robot decides to move on the spot, its whole body, and obviously the sensor which is on its front, moves. So there are 2 wheels underneath this robot, and it can choose to turn on the spot. All right? Okay, carry on.
The ability to infer, once it's detected that it's moving closer, then by its current trajectory, that's how you detect transitions. So basically, in terms of like doing this code, yeah, you take 2 readings, and from those 2 readings, you plot a course, and if that course intersects with the robot, then it would move. Or if it's concentrated every time, the distance. I think how we figure out whether it's create a line it's not the motion of the thing is accelerated.
Rate at which it's approaching.
Based on where its motion rate
It's a linear function. So there's not a time to robot in that position.
Well, just think, well, I don't know how fast it goes. How fast are these dolphins? Does it matter how fast?
How fast they move?
Is it random or?
Let's say they move about the same speed as the robot. I don't think it really matters for this example.
As long as they're all fast, right? You just need to, yeah, I guess as long as the robot can escape fast.
Okay, it's gotten kind of quiet, so you must have all solved this problem. Do we have some solutions out there? How does the robot distinguish between these three cases? Yep.
It senses the object when it's in a certain radius, and then
How does it sense the object?
with the ultrasonic sensor.
So,
So it detects how far away the object is from it.
okay, but in all three of these cases so far, the robot cannot detect these objects. So let's get a little more detailed here. How does it detect the object? Sorry? Pivot, right? So it's got to start moving. So a robot moves, and then what happens?
It moves and then it will detect the object.
How? How does it detect the object? The ultrasonic sensor, what about the ultrasonic sensor will tell it that it's detected the object?
Returns a distance that's less than 2 feet.
Absolutely, right? So it's turning, the robot starts turning, the robot knows it's turning 2 feet, 2 feet, 2 feet, bam, less than 2 feet, right? So when you started your description here, you said the robot detects the object, which is shorthand for what's actually happening, right? So let's try and use the latter kind of language, sensor motor language. The robot acts and it gets this sensory repercussion, which means this. Okay, so the robot's turning, turning, turning. Suddenly the distance drops to less than 2 feet. What does the robot do now? Does it know whether it's in danger or not?
Wouldn't it, the timer have to start so that it could see in another matter of seconds or milliseconds, whatever, if the object's moving closer towards it?
Okay, so the robot could start the timer the moment that it sees the object. And what's it looking for at that point?
Increased or decreased distance.
Decreased distance, right? It was less than 2 feet, and now it's looking to see whether it's less than 2. Is that working? There's a detail that's missing here.
Maybe I should take one more measurement so that I can see it. Like in the third case there,
Okay.
it would be able to then see if that curve is meaning that the object is passing it.
In this third case here,
Yeah.
okay.
Maybe the 3.
So maybe it's got to take a few readings, right, over time.
In the third one, though, couldn't it just like sense that it's the object's right there, and then because it's leaving its field of vision,
How does the robot know the object is leaving its field of vision?
all of a sudden it goes back to 2 feet.
Aha. So the robot is moving, moving, moving. Distance drops to less than 2 feet. And at the next time step, the reading goes back to 2 feet. What does the robot do in this case?
Stay.
Sorry?
Doesn't it stay? Because
It could, but that's not a good idea in this case, is it? In the first case, yes, this one here. So we might have already stumbled on a solution, right? So I start moving 2 feet, 2 feet, 2 feet. Suddenly the distance drops to less than 2 feet. And then it goes back to 2 feet. Ah, I'm safe. Is that good enough?
Did it pass it?
Sorry?
Did it pass the object? It wasn't.
You tell me. From the robot's point of view, this is the idea we're trying to investigate here. You're trying to put yourself into the robot's point of view, right? Put yourself in the robot's shoes, the robot's wheels. All the robot ever gets in its whole life is just a single number from one time instant to the next, and possibly timing information. It's got to try and use that information to figure out something about its external world.
rotating the entire time to follow the object? I
It-
don't quite understand what
Okay.
the abilities are.
So the capabilities are that the robot can choose to move. So the robot could choose to just keep turning in a clockwise motion on the spot at constant speed if it wanted. Or it could choose to rotate in the other direction. Or it could choose to rotate until its sensor is less than 2 feet. It's up to you. You're programming the robot. It can change its actions based on nothing. It can just keep doing the same thing. It can change its behavior based on the timer and or the sensory information. To keep this simple, let's assume that it can just turn on the spot for now. It's got to distinguish between these dangerous and safe situations. How does it do so? Let's maybe start with the first case, which is a little bit easier. The robot is turning, faces the object, distance drops to less than 2 feet. The robot chooses at that time to stop moving, and it continues to see the distance dropping. In that case, the robot is pretty sure it's in trouble, right?
Isn't the first one, it's safe because the object.
Oh, I'm sorry. Yeah, you're right. I got the wrong one. So maybe it stops here and sees that the distance is less than 2 feet, but whatever that distance is, it's increasing. The robot knows it's safe. In this case, it also stops and sees that the distance is decreasing and knows that it's in danger. So this seems to be a pretty good solution. Move until distance is less than 2 feet, and then pay attention to how the distance is changing. Don't even need the timer.
Because it's constantly recording the distance, can it kind of get an idea of, like by triangulating, I guess,
Yep.
What direction it's actually going in?
Yes, so in these two cases it can, right? It can figure out whether the object is approaching or moving away from it. But if the object is moving obliquely to the robot, meaning the object is here and starts and moves in this direction, if the robot turned clockwise and pointed at this object and stopped moving, it's in trouble, right? So this simple little program we've sketched out for the robot is not sufficient.
Why would it be in trouble if it just focused on that? Because the second it leaves its field of vision, wouldn't that mean it's not going to hit it?
Good question, right? So the robot says, okay, I'm going to modify my program a little bit. Move, see the object stop, and at the next time instant, my vision goes back to 2 feet. Therefore, I'm safe. Is that good enough?
Unless it curves.
All right, let's assume it doesn't curve, straight lines. It's not quite sufficient.
So it can't follow the object?
It could, we just haven't added that to the program yet. So it's definitely not safe, right? So this oblique angle is safe, but this oblique angle is not safe. So just because the object has left its field of view,
But wouldn't it, if it turned towards that, wouldn't it be able to still see it if it was going at that angle?
okay, so maybe the robot turns towards it. How does the robot know to turn towards it? All it knows is that it got 2 feet, and then it got less than 2 feet, and then the next third time instant, it went back to 2 feet. This robot does not yet know which direction the object has left its field of view. So which way does it go?
Well, if the robot was continuously spinning,
Ah,
it would read the distance at one point in time,
okay.
and then it would read the distance at another point in time. And then maybe it could stop spinning, move away, and then start spinning again.
Possibly, right? So again, there are lots of solutions to this problem. What I'm trying to impress upon you is it's tricky because it's hard to put yourself in the robot's shoes, right? We say, it should turn towards the object and track it to see whether it eventually, the object starts to move away from it. But we haven't yet figured out how the robot knows which way the object is even moving in, right? All it knows is 2 feet, less than 2 feet, then back to 2 feet. Here's one possible solution, which is that the robot just turns in a clockwise manner at a constant speed. And as it does, it's running the timer. And in this example, it wasn't 2 feet, it was 30 millimeters. 30 millimeters, 30 millimeters, 8 millimeters, 30, 30, 36, 30, 30, 30, 30, 40, and so on. This is what we might see. We might see the object approaching the robot, but this is what the robot sees. So depending on the time interval between these two readings, so this is like the radar beam that's moving around and pinging whenever it hits something. If that time interval is constant, the robot keeps turning around and around, and it keeps getting a less than 30 millimeter signal at a constant time interval, what does that mean? It's getting closer, more specific than that. Well, we don't know if it's getting closer. Well, in this example here, yes, it's getting closer. If at every 1.5 seconds, it always gets a less than 2 feet reading, what does that mean about the object?
Maintaining the same velocity would mean that it's like going parallel to the object, right?
That's that the object is moving parallel or in towards the robot, right? So it's always hitting, the robot's sensor is always hitting the object at the same angle of the clock, right? The robot is turning at a constant velocity. The robot has decided what to do. It's moving at a constant velocity. Its timer is just running, and it sees every 1.5 seconds, I get a reading that's less than 30 millimeters. That means whatever that object is, it's always at the same angle relative to me.
Isn't that kind of wasteful for energy though? Like constantly having a robot.
Yes, we could. That's all. Maybe not a practical solution.
Yeah.
Yes, that is true.
Lithium-ion batteries aren't good enough.
Yes, perhaps. Okay, so it's seeing this object at a constant time interval, and it notices that every time it sees the object, the distance is less. It knows it's in danger, right? The object is always at 2 o'clock relative to me, and every time I see it, as I spin, every time I see it, it's closer. I'm in trouble, right?
Can you just do like have it turn to the left and turn to the right and check to see where the object is?
Yes.
So you can just keep tracking
Yes, we could actively track the object, right? In this case, if it sees the object at 2 o'clock and every time it sees it, the object is further away, then the robot also knows that it's safe. If the robot turns at a constant velocity and it sees the object at a non-constant time interval, what does that mean? It's not angled directly towards the robot or away from it. It's moving, right? I see it at 2 o'clock. The next time I come around, I see it at 3 o'clock and 4 o'clock and then 5 o'clock. And I also see that the distance is different. If you were to plot that as a line, on one side of the line, the robot will know that it's always safe, and on the other side of the line that it's always in danger. That's one possible solution. The other one is to actively track the object. This is, in the field of robotics, a pretty trivial example, but at least for me, this is hard to do because you have to think about what the robot has at hand, right? So this is often known as the frame of reference problem. Here it is, the frame of reference problem. The frame of reference problem is a problem because when we observe an animal or a robot or an app, we're seeing it from our point of view. Oh, the robot can see that the object is behind it. The robot has no idea about behind or in front of me. All it has is distance and timing information. We have a particular view onto the problem, which is very different from what the robot sees, right? When your user is looking at your app, they say, oh, the app can see that I'm doing ... The app may or may not be able to see that. The app is probably seeing something like this and may or may not be able to infer what the user is doing. This is a very difficult bias built into the human cognitive system, which is this frame of reference problem. I'll come back to the superbot in a minute. I want to just end with the frame of reference problem today. We've run out of time, but this works with people as well. If we had more time, I would get you to stay where you are and turn in your seat to look at the students behind you. Then I would get you to come up to the front of the room and stand where I'm standing and figure out which students here are occluded from my field of view. So I know which students are occluded from my field of view. You don't. The students in the front row will usually do a much better job than the ones in the back row. Why?
Closer to your position.
You're closer to my position, right? So your frame of reference is more similar to my frame of reference than your frame of reference is to my frame of reference, right? It's hard to put yourself in my shoes, even though we're both humans. Much harder to do if you're trying to infer the frame of reference or what a robot or an app can see. Okay, we've run out of time, so I'll stop there. Deliverable 8 is due tonight. You have a quiz due tonight, and I will see you on Friday. Thank you.